Welcome back to Coding an Emulator in a High-Level Language. This session we're going to complete the work that I did in last time, which was branches and jumps. We spent a lot of time figuring out bugs and working our way to assembling jumps and branches, and now it's time for us to actually implement the emulator part, actually executing these instructions. And we're also going to fix a very important bug that I have been hand-waving my way around, but we need to address it before we go much further. So let's jump into the code. So in our emulator tests now, we need to implement tests for the memories, loads and stores that we implemented last time, and also the branch and jump instructions. So the first thing we'll do is create a test for a load of a byte. And we'll implement load byte. And what it will do is it will set up some initial state for our test. The first thing we'll do is in our memory we will write a byte at address 8, and the byte will be 42 hexadecimal. Then we need to set up a register, so we'll say that the register 4 will have the value 4, and the register 5 will also have the value 4. That's our initial state. Then we're going to assemble a load byte instruction, and the load byte instruction is going to load the byte into register 4, and it's going to use register 5 as the base register and then an offset of 4. So what this will end up doing is reading the contents of register 5, which is 4, then it adds the offset 4 to that 4, giving a result of 8. That is the memory address that we're going to be reading the byte from. We then read the memory at address 8, which should contain a 42, and then that 42 should be written into the byte 4. So at the end of this operation, then we should see a 42 written in our inside of register 4. But I just had a thought, and that is that load byte is sign extending, so we need to make sure that the value that we read does get sign extended. So I'm going to change the byte that we're writing to 82 hexadecimal. Now this is an 8-bit quantity whose high bit is set to 1. So when this gets read by the load byte instruction, that the highest bit of 82 will then be extended into the full word that gets stored in the register. So the end result should be 0 FF82, and that is what's going to be stored in the emulator register. So here we see the high bit of 82 is set, so therefore the remaining bits in that 32-bit word are going to be sign extended, and this is what we expect to see. Let's try running this test, and of course it will fail because we haven't implemented a handler for the load byte instruction. So let's hop over to the manual and go down to chapter 37 where the load byte instruction is located. And so we should now have an error. It's complaining about major opcode 11, which we haven't implemented yet. So let's do that. So the major opcode is 1111, and we now need to fetch a funct3 because we need these 3 bits, the funct3 bits, to decide which one of the load instructions we wish to carry out. So now we have the function. Now we can also, in fact, extract the source 1 and source 2 and the immediate fields, because they're always going to be the same. So let's go ahead and extract those 3 fields, except that source 1 is not, or source 2 is not what we want. We want the immediate field. So let's see if we can steal that from somewhere else. There we have it. So it's a signed value that we wish to extract, because the value that we're getting is a signed value. So there we go. So now we have the base register, which is in source 1, the immediate value, which is in the slot for the immediate bit field, and then finally the destination is the bit field for the destination. So now we can check the funct3 value and see what we got. So in the case of funct3 equal to 0, that's our load byte scenario. So what we need to do now is construct an address by fetching the base register from the registers. So let's go ahead and do that. And then we add the immediate value. This gives us an effective address. And this is probably a computation that will be repeated, so we might as well put it here. So now we have an effective address, great. And now we need to read the byte at that address. So we walk up to our memory and we say read byte at the address. Let's cast this to an unsigned integer, since addresses are unsigned quantities. So that cast is no longer necessary. So we read the byte, and then we have to this is going to be an unsigned C# byte. We need to turn that first into a signed byte, and then we will take that and store it into the destination register, like this. And then we break. And we need to change the effective address to an unsigned int. And that should do it. Then we'll add our usual invalid operation for any unhandled cases. And then we should be good to go. All right, let's run our unit test and see what happens. Okay, we have an overflow when trying to convert. I see, the unit test itself has a problem. Let's go fix the unit test. Let's cast this to an integer. And we need to make it an unchecked cast because C# is paranoid with good reason. Let's try that again. And we have a green flag. So this means that the 82 byte that was read from memory is sign extended into this large negative number. Fantastic. So we can now do the same thing for load word and load half word. We might as well just take care of those two cases so that we don't have to think about them. And in this case, let's write a few more bytes into memory. Now remember that we have to write these bytes in little endian. So what we'll do is we'll write 8 at byte position 9. We write the high byte, which will still be with a high bit set, and then a 7, and then a 6 and a 5. And reading that half word should give us 8765 if everything is done correctly. And similarly for the wide word, here we don't have any sign extension because we'll be writing 4 bytes to memory. So we'll just write them in a nice pleasing pattern. 1, 2, 3, 4, 5, 6, and then change the address to 9, A, and B. So in this case, I expect we no longer need to cast this. I expect the 1, 2, 3, 4, 5, 6. And let's change this to 7, 8. So we have a nice recognizable pattern. And in this other case, we're good to go. But this is an LH, not an LW. That's an LW. So if we now run all of our tests, we should get a failure complaining that we haven't implemented neither LH nor LW. Yeah. So let's implement them. So case 1 is LH. So if we have a C1, then it's an LH. If it's a 010, then it's a LW, load word. So when we see the func3 value of 001, that means that we are loading a half word. So in this case, we change the cast to a short, which in C# lingo is a 16-bit but here we have a problem. We need to read a 16-bit quantity, and we haven't implemented that. So let's create a read LE word 16, and then we have to implement that functionality. We'll just take the LE word 32 that we already have working and downsize it. And that ends up being the code that we needed. And let's remind ourselves that LW was 010. Let's finish that case. So now we have, why don't we leave a little marker here as well to indicate what these things are. Future programmers will appreciate that. So in this case, we do need the 32-bit quantity. So depending on which operation we are doing, we're either reading a byte, a word of 16 bits, or a word of 32 bits. And in this case, we don't need a cast. The word will be the correct size. Well, we do need a cast to change its type, but we don't need a sign extend it. Right, so that should do the trick. Let's see if everything passes now. It does. And then we can finally implement the last two cases of load, which are going to be the unsigned variants of load byte and load half word. So we'll start with load byte and implement load byte unsigned. So in this case, we don't expect all these FFFFs to appear. Instead, we just want to see this value appear in our register. And make sure that we use the new instruction. And then for LHU, we do the same thing. Well, first we have to copy this. There. And in this case, again, we don't expect any sign extension, just a nice 0 extension, because this is being read as an unsigned number. Okay. Let's try running those tests, all these tests. And now we have to implement them in the emulator itself. So unsigned byte is the bit pattern 4, and the unsigned half word is bit pattern 5. So we'll copy these, but we'll add 4 to both of the cases and add a comment. And in this case, we read our byte and we do not sign extend it. We 0 extend it by basically just letting the compiler extend it for us. And here, the unsigned word, we cast it to U short. And that forces it to be an unsigned short, a 60-bit unsigned integer, and then that gets stored into our register. So that should implement those two. Nice. So now we're done with all the the load functions. So now we can start working on store. So let's write the unit test for a store. So it's going to look very similar. Let's start with store byte and work our way up. So we'll use this as a template, but we'll modify it. So what does store byte do? Well, in this case, we're going to assume that the memory at address 8 is our destination. We're going to use the same register values, except here, recall that the store byte instruction takes the value that it stores as its first parameter. So our register 4 is the value that we want to store. So let's store the value 82 into memory. And we'll get rid of this because we won't be writing to memory in our test, but we will be verifying that that value actually got written. So here we have, in fact, let's put a bigger number into our register 4. 1, 2, 3, 4, 5, 6, 7, 8. Now when we say store byte, what will happen is we only want to store the least significant bits of this word the 8 bits at the bottom of this word. So that is what is going to be stored at address calculated from taking the contents of register 5, which is 4, and then adding an offset of 4, giving us the address of 8. So at address 8, there should now be a 7/8. But the other locations of memory beyond address 8 should be zeros. So we can verify this by reading in the word at address 0 or address 8. And that should give us the bytes, not only the byte at address 8, but the bytes at address 9 and 10 and etc. And we expect only the 7/8 to have been written. So we expect only a 7/8 to come back. Good. So let's try running this test and see whether it passes. And it won't, because we haven't implemented store yet. It's another major opcode that we haven't implemented. Let's go and look at the spec for this. It's this major opcode. Yep. So let's add a case for him. There he is. Let's put an actual 0. Okay, so just like before, for the load, we need to get a funct3 to understand which of the different extractions we're doing. In fact, we'll steal all of these. Now remember, confusingly, the data in the slot that we're calling DST is actually going to be the data that we're storing. It is a confusion. It probably should be called operand 1. I'm not going to change that now, but it is confusing. I am the first one to admit to this. But we'll live with it for the time being. But we've extracted the function 3, which will tell us which size of storage we'll be storing. And then src1 will contain the base address. And aha, here comes the first, or a new challenge now. We have to recall that for the store function, the offset is broken up into 2 pieces that we have to reassemble. Let's go to the manual and look at what a store function is laid out, or what its layout is. So a store type needs to fetch some bits from the low word, the lowest 5 bits from here, but then the remaining bits from up here. So we have to change this immediate function so that it, instead of just extracting from a single bit field, we have to specify multiple bit fields and then extract the value from them. I'm actually going to add a static member function or a static method to bit field that allows us to extract a value from multiple fields. So this is how I'll do it. It's a static function. And we'll pass it an array of bit fields. So we'll start with a result, and then starting at the So these fields will be ordered in the order that we wish to read them. And what this function will do is it will read the most significant bits first, and then shift them to the left, and then read in the next sequence of fields. So we'll do it like this. Iterate through the fields. Take the existing value of the result and shift it to the left by the current field. Its bit width. So now we've made room for that, and then we will OR in the bit vector field that we extract. Let's make this an unsigned result for the time being, because we're bashing bits together. We don't want to get involved in sign extension while we're constructing the bits. So we've just read one field, and we then loop until we have received all of the bits. We should also keep a track of how many bits we have loaded in total. So the number of bits is this bit width. So we can say, yeah, thank you IntelliSense. That's exactly what I needed to do. And then at the end there, we're going to do a magic trick. And you'll have to take my word for it, but what I'm about to do is actually going to convert perform a sign extension. Perhaps if there's any interest, I can explain in more detail how exactly this trick that I'm about to do performs its duties. But for now, what we're going to do is just implement this as we'll create a mask, which is the C bits 1 shifted to the left by C bits minus 1. And then what we're going to do is create a result is equal to result XOR m minus m. And believe it or not, that will actually sign extend this number. Then finally we'll return our result, but casting it to a signed integer. So this should return the concatenation of these fields, but as a signed number. Adding a partially useful comment there. Nice. Okay, now let's go back to the emulator. Now the emulator has a way to read these multiple fields. Now we have to define the multiple fields. So let's create the bit field for this one. And it's going to be 2 fields. We're going to need a bit field that starts at 2531. So that's a 7-bit field. Yes. So the bit field that starts at 25 and has length 7. And then we need another bit field for this piece, which is at bit position 7 and length 5. Finally, we're going to create a little array consisting of those two fields, and we're going to call this bit fields for the S immediate. And it's going to be BF25L7 BF7L5. There we go. Let's not worry about that for now. So now we can use our new function to read those bits. So instead of this, we say bit fields extract signed, and we pass in our fields, which is going to be this value right here. So now we have an immediate value. And then recalling again that we have a counterintuitive naming here, DST. The first operand is actually a source operand in this case. We compute the effective address, just like for load, by taking the base register, which is at source 1. We add the immediate value that we just computed, and now we do a switch on the func3. And if it's a 0, then we know it's a store byte. So in the case of a store byte, we want to go to memory and write a byte. And the byte is at address, effective address, and the value is the contents of the register whose descriptor is dest. Again, the confusing naming convention here. So we'll say dest fetch the value of dest and then force it to a byte and then store that byte. And then we'll have a handler for the default case because we don't know. We haven't implemented the handlers for these other two yet. Alright, let's see if we can make this test pass. Let's challenge ourselves a little bit though, because I want that offset to be a little longer. So I'm going to go to my emulator test and change the offset to 1, 2, 4. And then that plus the 5 in, or the 4 in register 5 will result in an effective address of 128. So the byte 78, oh, sorry, is going to be read from the address 128, which is 124 plus the contents of register 5, which is 4. Let's run that again. Fantastic. So it looks like our reassembly of the fragments of the the immediate displacement or offset is correct. Now we can do 2 more tests for store byte or store half word and store word, and they should be fairly smooth sailing because they are going to be very similar. So let's write them. And then we're done with memory handling, and we can start looking at jumps and branches. So in this case, we are writing a store half word, and so now we expect the word when we read it to have stored only 5, 6, 7, 8. So that should be our new test. And then for store word, we expect the whole word to have been stored. Let's run these tests. And we get a failure because we haven't implemented these functions in our emulator yet, or these instructions. So let's quickly implement those. So we'll make a store half word and a store word, and then we consult the manual to make sure that we have the correct encodings, or decodings, I should say. So store byte was a 0. Now we have 001 will be a store half word, and 010 will be a store word. Great. So storing half word and storing word. And in the store half word case, we need to take the value and then write a little endian word 16, which we need to implement. And in this case, we'll cast the contents of the register to an unsigned short. And for the word case, we just remove the signedness of that register. Now we need to implement write word 32, which is going to be the little brother of this value. Let's copy both of these overloads. So it's a 16-bit write. And the value is going to be an unsigned short or a signed short. And we no longer need the 2 higher bytes. We just need those 2. So the code is a lot more compact. Okay, let's give this a run. Strictly speaking, we should be writing unit tests for the memory class, but in order to save time, I am skipping those tests. Excellent. So now at this point, I'm actually going to, let's see, let's try committing the changes that we have, because we have quite a few changes and I don't want to lose any work. So let's add those changes, and then let's see, implement emulation of loads and stores. Okay. But before we can proceed now to branches and jumps, we have to address the bug that I mentioned earlier, which is that we are making an assumption which the RISC-V architecture states register 0 always contains the value 0. But also, if you attempt to write to register 0, whatever you write is discarded. It doesn't get changed because register 0 always has value 0. But our current emulator actually allows you to write into register 0. So we will write a unit test to verify this and then fix the problem. So here is the add-I instruction. Recall that add-I takes 3 parameters: the destination register of 0, source register of 0, and then 42. So what this instruction would do is read the contents of register 0, which is always 0. We add 42 to that, and then we store it to register 0. But because register 0 is always supposed to be 0, this value should be discarded. However, and so we'll verify this. Register 0 should have the value 0. But if we run this test now, we'll discover that that is not true. Notice that the value in register 0 was actually 42, which is incorrect. All writes to register 0 are supposed to be discarded. And if we don't do this, then we fail. We do not adhere to the RISC-V specification, and a lot of instructions are dependent on register 0 always containing the value 0. So we need to enforce this. And there are multiple ways of doing this, but one lazy way is to just say we'll introduce an array of masks. And these masks are bit patterns that we will use the logical AND operator on every time we write to memory or write to a register. So let me illustrate what I mean. So we have this array of registers. Now we're going to create a private array of masks, reg masks. And then in our constructor for this class, we're going to initialize the register masks as follows. The masks for all of the registers except for register 0 are going to be all 1s. So for I is 1. So notice how we're skipping the first register, or the 0th register. And for each one of the other ones, we're going to set the register mask of that slot to the complement of 0. Now the complement operator in C# takes the argument, this word, and every bit that is a 0 turns into a 1. So this word, which is all 32 zeros, will become all 1s. Then, whenever we write to our register, we actually have to mask it with that value. So it makes sense to change all of these assignments to a method called write register. And we should disallow writing to the register's array directly. So what we're going to do is make the register, just remove all the places where we call registers.store, like here. So instead of making this direct storage into an array, we're going to introduce a method called write register. We'll pass in the destination and implementing this method will be as follows. So we take and find the mask, and then we take the we store the value of value, but masked with the mask value that we fetched. So for all registers other than register 0, that mask will be all 1s. And remember that the AND operator will allow bits through if the bits is 1. So whatever value is in value will be ANDed with all ones, which means that the value will be untouched and it will go straight into the registers. But if you are passing in a register 0, then the reg mask for that particular register will be 0, and that 0 ANDed with any value will always return 0. In effect, we're destroying whatever value is in value, and we end up writing a 0 back into the register. So the net effect is that the value of register 0 will always be 0. But we have to now be very careful about any place where we're storing registers. They have to be replaced with write register. So let's go ahead and find those places. And there's quite a few now. We've managed to implement a bunch of functions. And then here's another one. And here's more. Now these are store operations, so in this case we're not concerned. But I think that's it. All the places where we are writing the destination register have now been replaced. So if we now run our tests, we should have succeeded in fixing the bug. Excellent. Now the reason why this is so important is because we're about to embark on implementing the jump and link instruction that I talked about in my previous session. And jump and link is an interesting instruction because it does a little complicated little dance. So recall that the jump and link instruction takes a offset, which is a 21-bit quantity, which allows us to jump around a megabyte around the current location of the current instruction. But what it also does as a side effect is, before it transfers control to that location, it saves the address of the next instruction into the value the register whose descriptor is RD. So if I'm at address 42 and I encounter a jump and link instruction and the destination register contains 4 for register 4, then the address of the next instruction will be stored in register 4 after this instruction is executed. So even though my control flow has jumped to some other part of the program, the register that is designated by this slot will remember where we came from. And this is critical for implementing calls and returns. We're not going to implement calls and returns in this session, but it's worth mentioning what the purpose of that linking register is. Now, if you are doing a jump to a target and you don't really care about remembering where you came from, then it's useful to be able to just discard the value that is computed by the jump and link instruction. And here in the spec, it's stated clearly that if you're just doing a plain unconditional jump and you don't care about returning back to where you jumped from, then you can encode the jump and link instruction by just putting a 0 in the destination. So this is exactly what we'll do. We will implement the jump and link instruction. And to do this, we will have to go to our emulator and add another test. So, how do you write a test for this? Well, we will start by creating a little program. And I'll specify that we're going to be storing or discarding the next address, the link address, because we are not going to do calls today. So what should we do? What we'll do is we'll write a little program that does the following. It will set into the register 4, we're going to put the value 1. So register 4 gets the value of adding the contents of register 0 with immediate value of 1. So 1. And then we're going to go and do a jump and link. And remember now the destination register is 0, so that's where we'll store that. And then the destination that we want to jump to is unknown as yet, but we'll get there. Then we're going to provide a test path here. So if we reach this, then for some reason the emulator didn't work. So what we want to do now is set the value in register 4 to -1. So that's an error condition. It tells us that, nope, sorry, you failed. Then we will we'll have to compute where we wish to go to. So we'll create a dummy instruction that will just do nothing. This is a dummy function where we take the contents of register 0, add 0 to that, and discard it by writing it to register 0. So this is just a placeholder instruction so that we can jump to it. Now remember, we have to compute the offset from this instruction, which is at address 4, because this is at address 0, address 4, address 8, address 12. So the offset to get to this instruction here, the no operation, is 8. So that's how we do that. So this jump and link instruction will jump to the relative offset of 8, which is going to be this instruction here. So if the jump and link instruction is correct, then at the end of this, our register 4 should have the value 1 and not -1. So then we will assert that. All right. Now let's emulate this. And this will fail because we haven't implemented the major opcode for the jump instruction. So let's go to the jump instruction, which is down in here. So this is our major opcode. And there is no subfunction, so now all we need to do is read the destination register, which is this value. But then also, what we need to do is extract the very complex jump destination offset, which is broken up into 4 pieces. So we'll use this diagram here to help us reassemble that word. So we'll need to grab the pieces in this order. First, the most significant one at bit position 31. So we'll create a bit field at position 31 of length 1. The next bit field is at position 12, and it has the length 8. Yes. The next fragment is the single bit at bit position 20. And then finally the fragment here starting at bit position 21, and which is 10 bits long. And then we will create the array of fields for the jump immediate, which is going to be the concatenation of these bit fields in order of descending importance. So BF31 L1, BF12 L8, BF20 L1, and BF21 L10. There's our bit field. So now we can actually implement our jump and link instruction. So we'll say that the immediate displacement is going to be bit field extract signed. We'll take the uinster, and then the bit fields jump immediate, like that. So there's our displacement. So what do we need to do here? Well, the first thing we need to do is compute our next value, or the next address, the address of the instruction after the current instruction, because that's what we have to write into the destination register. So let's see, do we have our current address? In fact, here we have taken the address and added it to IPTR plus 4. So IPTR at this point has the address of the next instruction. So I'm not very happy with this, however. So what I'm going to do is I'm going to do a quick refactoring. I'm going to call this IPTR next. And then at the end of this function, I'm going to set IPTR equals IPTR next. And the reason will become apparent shortly. So IPTR next is the address of the next instruction if we do not transfer control. But it also will be the address of the next instruction. So even in this case for our jump, we can now write the register with the adder next. What did I call? Oh, IPTR next. And let's cast that into an integer. So if the destination register happens to be 0, this will be discarded, but otherwise we will remember where we jumped from in that register, and that will be useful later when we're doing jumps or calls. But we actually have to implement the jump. So here, what we want to do now is take our current address, which is IPTR. The change that I just made is, ensures that IPTR still has the current instruction address. And I'm going to add the displacement IMM to that. And then I'm going to take the result of that addition and assign it to IPTR next. So if we look at the code that we are going to be testing, the jump and link instruction will take this 8, which is im, and it's going to add that to IPTR, which is 4, and that will give us IPTR next of 12. And then we assign that to IPTR and return that to the caller. So we should be then landing on instruction at address 12. So let's give that a try. We have a failure. Why the sadness? Okay, so it looks as if we failed to execute this transfer. So let's take a look and see why that is. We'll put a breakpoint here and then debug this one test. So first of all, let's make sure that the displacement is correct. And that's a 4. Aha! And here's a subtle issue. Notice how when we extract the bits out of the instruction fields, you'll notice that the encoding never mentions bit 0. Now bit 0 is always going to be 0 for any jump on a RISC-V processor, because all the instructions always have an address which is evenly divisible by 4. So the lowest bit of the instruction will always be 0. So there's no point in encoding it in the instruction, because it would be a waste of a bit. So therefore, what we need to do before we add the displacement is we have to reintroduce that bit, and to do that we just take im and we right shift it by a single bit. That will shift all the bits over to the right, and now we have an extra 0. If we run this, we now have a successful test. How exciting! So we're almost done. We only have to implement the B&E instruction now. So let's go ahead and write a test for that. I will steal the existing code for jump and link, and then we'll write for B&E. So we'll use something similar here. What we'll do is we'll say branch if not equal. So currently register 4 will have the value 1. So if we say that register 4 should not be equal to the value of register 0, which of course is always 0, if these two registers are not equal, then we want to jump 8 bits. Or 8, we want to jump 8 bytes ahead, which will skip the -1. So Initially, register 4 has the value 1 because we add 1, the immediate value 1 to the register 0. We then check the 1, which we stored in 4, and compare it to the 0, which is always present in register 0. And because those two are not equal, we should jump to address 8. Alright, great. So let's run this program. And we expect a failure because we haven't implemented BNE or any of the other conditional functions or conditional branches. So let's go to the spec and find out what we need to extract. It's this major opcode. And we need to extract source 1 and source 2, and then the 4 bits or the 4 fields that constitute the displacement of the jump. So we'll steal the code for source 1 and source 2. We also need funct3, so we might as well grab that. And then we'll do the same thing as with the jumps. We need to create our immediate displacement, which is a bit field, assigned bit field that we'll extract with our bit fields. And this time it's bim for byte im. And again, if we look closely at the bits that we're extracting, notice that we never mention bit 0. Bit 0 is always going to be 0, so it's not encoded in the instruction. And so we have to be careful about that. But now we have to build our fields. And so, just like before, we need to put these together in the right order. Let's go back to the section where these are described because it's a little easier to read. So we're encoding a B type. So the most significant bit is stored in bit position 31. We already have a field for that, so we can reuse it. Then this next one is a single bit at position 7. So we'll grab the single bit at position 7. And then we want the bit field that is at position 25 of length 6. So we'll have position 25, length 6. And then finally we'll have the bit starting at position 4. Or 8 and of length 4. Nice. So now we need to create the array of all the bits smashed together, most significant to least significant. So bit position 31L1 we already knew. Then we have bit position 7 L1, 25 L6, and 8 length 4. Groovy. So will it work first try? Well, it won't because we haven't implemented the actual jump. So let's go here and we have to switch on funct3 again. And the case for our instruction B and E is func3 should be 001. So in this case, we need to extract the value from source or register 1, which is described by src1. So we'll say registers src1. If this is not equal to registers of src2, then we do the transfer. Otherwise, we fall through. We don't do anything. So if this is true, then what we want to do is the same as we did before. We want to take the IPTR next and adjust it by adding the immediate displacement to the current position. And then we'll add a guard for the other unimplemented cases. And these we can fill in later. And we are good to go. Let's run this test and see whether it works. And we have a green bar. So amazingly, we now have implemented all of the instructions in such a manner that if we were to feed the output of our assembler to an actual RISC-V core, it would execute them in the same way as our emulator does. So we are faithfully emulating a RISC-V core, and we have a handful of instructions now. So with that, I will conclude this session. Next time we will look at calling and returning. That will be an exciting topic. We will also talk about calling conventions. And don't worry if you've never heard of that term before, it will be explained. Until then, have a good one.